Hello, and welcome to Dreamy Discovery, your cozy corner of the cosmos where we explore the wonders of science in a way that's soothing, fascinating, and just relaxing enough to gently lull you toward dreamland. As your eyes grow heavier and the world softens into a quiet hush, let yourself drift deeper into this gentle calm. In the quiet hours before dawn, when the world lies still and the stars shine brightest against the velvet sky, there exists a force so fundamental, so ever-present, that we scarcely notice its gentle pull. It draws the morning dew to the earth, guides the moon in its eternal dance around our planet, and keeps our feet firmly planted on solid ground. This invisible hand that shapes the cosmos has captivated human minds for millennia, leading us through a journey of wonder, discovery, and profound understanding that would reshape our very conception of the universe itself. Long before the first written word, long before the rise of civilizations, ancient peoples gazed upward at the celestial tapestry above and wondered why objects fell toward the earth, while the moon and stars remained suspended in their heavenly realm. In the fertile valleys of Mesopotamia, where the Tigris and Euphrates rivers carved their ancient paths, early astronomers recorded the movements of celestial bodies on clay tablets, noting with careful precision how the wandering stars, what we now call planets, traced their mysterious paths across the night sky. As you settle deeper into comfort, let your mind drift back to these earliest moments of human curiosity, when the boundary between science and mythology was as thin as morning mist. The ancient Babylonians, masters of mathematics and astronomy, developed sophisticated models to predict eclipses and planetary motions. They understood that the heavens followed patterns, that there was order in the apparent chaos of celestial movement. Yet they could not explain why a stone dropped from their ziggurats fell straight down while the moon continued its endless circuit overhead. In their creation myths, they spoke of cosmic battles between order and chaos, of gods who held the world in place through divine will. The concept of gravity, as we understand it today, was still millennia away, but the seeds of questioning had been planted in the fertile soil of human consciousness. As the centuries passed like gentle waves upon an ancient shore, Greek philosophers began to approach these questions with a new kind of thinking. In the marble halls of Athens, where olive trees cast cooling shadows and the Mediterranean breeze carried the scent of distant lands, thinkers like Aristotle pondered the nature of motion and the structure of the cosmos. Aristotle, whose influence would span more than 1,000 years, proposed that heavy objects fell faster than light ones because it was in their nature to seek their proper place in the cosmic order. He envisioned a universe where the Earth sat motionless at the center, surrounded by crystalline spheres that carried the moon, sun, planets, and stars in their eternal rotations. This geocentric model, elegant in its simplicity, satisfied the human need for order and purpose. It placed humanity at the center of creation, with the heavens arranged in perfect harmony around us. For nearly 1,500 years, this view would dominate Western thought, taught in the great universities of medieval Europe, and accepted as both scientific truth and religious doctrine. As the night deepens around you, imagine the comfort that such a worldview provided, a cosmos where everything had its place, where the motion of celestial bodies was governed by divine perfection rather than the mysterious forces we now call gravity. The Roman Empire, inheritor of Greek learning, preserved and transmitted this ancient wisdom even as their legions marched across Europe and their engineers built roads and aqueducts that would endure for millennia. Roman scholars like Pliny the Elder compiled vast encyclopedias of natural knowledge, including observations about falling objects and celestial motions. They noticed that projectiles followed curved paths, that water flowed downhill, and that the tides rose and fell in rhythm with the moon's phases. Yet they lacked the mathematical tools and theoretical framework to connect these observations into a unified understanding of gravitational force. As the Western Roman Empire crumbled and Europe entered what historians once called the Dark Ages, the torch of learning passed to other hands. In the great libraries of Baghdad, Cairo, and Cordoba, Islamic scholars preserved and expanded upon Greek knowledge. They translated Aristotle's works into Arabic, adding their own observations and calculations. Muslim astronomers like al-Battani refined measurements of planetary motions, while scholars like Ibn al-Haytham, known in the West as al-Hazen, developed new methods of experimental investigation that would later influence European science. During these centuries of Islamic scientific flowering, from the 8th to the 13th centuries, scholars in the House of Wisdom in Baghdad and other centers of learning grappled with questions that would eventually lead to our modern understanding of gravity. They studied the works of ancient Greek mathematicians, translated Sanskrit texts on astronomy from India, and conducted their own careful observations of the heavens. As you drift deeper into relaxation, picture the oil lamps burning late into the night in those medieval libraries, their flickering light illuminating manuscripts filled with geometric diagrams and astronomical calculations. The Crusades, despite their violence and religious fervor, inadvertently served as conduits for the transfer of knowledge between Islamic and Christian worlds. European scholars traveling to the Holy Land encountered translations of Aristotle's works that had been lost to the West for centuries. They returned home with new ideas about mathematics, astronomy, and natural philosophy that would gradually transform European intellectual life. The University of Paris, Oxford, and other medieval centers of learning began to incorporate this recovered knowledge into their curricula, setting the stage for the scientific revolution that was still centuries away. In the 13th century, a Franciscan friar named Roger Bacon conducted experiments with lenses and mirrors in his cell at Oxford, laying groundwork for the scientific method. Though his work was often viewed with suspicion by church authorities, Bacon insisted that knowledge of the natural world could be gained through careful observation and experimentation, rather than purely through logical deduction from accepted principles. His approach represented a subtle but crucial shift in thinking, from accepting the world as it appeared to be to questioning and testing our assumptions about natural phenomena. As the medieval period gave way to the Renaissance, European society underwent profound changes that would create the conditions necessary for revolutionary advances in our understanding of gravity and motion. The invention of the printing press in the mid-15th century meant that scientific works could be copied and distributed more widely than ever before. The fall of Constantinople in 1453 sent Greek scholars fleeing westward, bringing with them ancient texts that had been preserved in Byzantine libraries. Trade routes to Asia brought not only silk and spices, but also new ideas and technologies. In this ferment of intellectual activity, a Polish astronomer named Nicholas Copernicus was quietly working on ideas that would shatter the medieval worldview. Born in 1473 in the town of Torun, Copernicus studied at the University of Krakow and later in Italy, where he encountered the mathematical works of ancient Greek astronomers. As you allow yourself to sink deeper into peaceful rest, imagine young Copernicus walking the cobblestone streets of Renaissance Krakow, his mind already turning over the problem that would occupy much of his life. How to account for the observed motions of the planets in a way that was both mathematically elegant and astronomically accurate. The Ptolemaic system, which had dominated astronomy for over 1,000 years, required increasingly complex arrangements of circles upon circles to account for the observed positions of the planets. Copernicus realized that many of these complications would disappear if he placed the Sun, rather than the Earth, at the center of the planetary system. This heliocentric model was not entirely new. The ancient Greek astronomer Aristarchus had proposed something similar. But Copernicus developed it with mathematical precision and presented it as a comprehensive alternative to the geocentric worldview. The implications of Copernican astronomy went far beyond technical questions of planetary motion. If the Earth was not the fixed center of the universe, but merely one planet among others, orbiting the Sun like any other celestial body, then humanity's special place in the cosmic order was called into question. Moreover, if the Earth was in motion, spinning on its axis and orbiting the Sun, why didn't we feel this motion? Why didn't objects fly off the surface of a rotating Earth? These questions would eventually lead to a deeper understanding of the force we now call gravity, but in Copernicus's time, they remained profound mysteries. Copernicus published his great work on the revolutions of the heavenly spheres in 1543, the year of his death. The book was dedicated to Pope Paul III and was initially received with more curiosity than alarm by church authorities. Its mathematical complexity meant that it was read primarily by astronomers and mathematicians rather than the general public. Yet it planted seeds of doubt about the accepted worldview that would eventually grow into a full-scale scientific revolution. The decades following Copernicus's death saw Europe convulsed by religious wars, political upheavals, and cultural transformations that created both opportunities and dangers for those who would challenge accepted ideas about the natural world. The Protestant Reformation had shattered the unity of medieval Christendom, while the discovery of the Americas had revealed that the ancients had been wrong about the extent and nature of the world. In this atmosphere of uncertainty and possibility, a new generation of natural philosophers began to question fundamental assumptions about motion, matter, and the forces that governed the behavior of objects both terrestrial and celestial. In Denmark, on the island of Hyven, a nobleman named Tycho Brahe was constructing the most sophisticated astronomical observatory the world had yet seen. Tycho, born in 1546, had witnessed a partial solar eclipse at the age of 14 and had been captivated by astronomy ever since. He spent the next decades making careful observations of planetary positions with an accuracy that would not be surpassed until the invention of the telescope. As the night continues to embrace you in its gentle arms, picture Tycho and his assistants working through the cold Danish nights, recording the precise positions of Mars, Venus, and the other wandering stars with instruments of brass and steel. Tycho's observations were so precise that they revealed small but significant discrepancies between the predicted and observed positions of the planets. These discrepancies would prove crucial in the work of his successor, Johannes Kepler, who would use Tycho's data to revolutionize our understanding of planetary motion and lay the groundwork for Newton's theory of universal gravitation. But Tycho himself remained committed to a compromise between the Ptolemaic and Copernican systems, proposing that the Sun and Moon orbited the Earth while the other planets orbited the Sun. The importance of Tycho's work extended beyond his observations to his method of conducting research. He insisted that theories about celestial motion must be tested against careful measurements, not simply accepted on the basis of philosophical arguments. This empirical approach, combined with mathematical analysis, would become the hallmark of modern science. Tycho also trained a generation of assistants in the art of precise observation, ensuring that his methods would survive his death in 1601. Among those who worked with Tycho was Johannes Kepler, a German mathematician and astronomer whose mystical temperament was combined with extraordinary mathematical skill. Born in 1571 in the Holy Roman Empire, Kepler grew up during a time of religious conflict and political instability. His early education was intended to prepare him for the Lutheran ministry, but his exceptional mathematical abilities led him to astronomy instead. As you drift deeper into the peaceful realm of sleep, imagine young Kepler walking the hills around his hometown of Weil der Stadt, gazing up at the stars and wondering about the hidden harmonies that governed their movements. Kepler's first major work, The Cosmic Mystery, published in 1596, attempted to explain the spacing of the planetary orbits in terms of the 5 regular solids of geometry. Though this particular theory proved incorrect, it demonstrated Kepler's conviction that the universe was constructed according to mathematical principles that could be discovered through careful analysis. This faith in the mathematical nature of physical reality would guide his later work and contribute to one of the most important advances in the history of science. When Tycho Brahe died suddenly in 1601, Kepler inherited his precious observations of planetary motion. For the next 8 years, Kepler wrestled with the problem of Mars, whose orbit seemed to resist all attempts to fit it into the traditional scheme of circular motions. The planet's observed positions differed from predictions by amounts that were small but undeniably real, differences that could not be dismissed as errors in observation given the quality of Tycho's data. After years of calculations, false starts, and moments of despair, Kepler made a revolutionary discovery. The orbit of Mars was not a circle, but an ellipse, with the Sun at one focus of the elliptical path. This discovery, published in 1609 in his New Astronomy, represented a fundamental break with ancient assumptions about celestial motion. For over 2,000 years, philosophers had assumed that the heavens were the realm of perfect circular motion. Kepler showed that the actual paths of the planets were more complex, but also more elegant than anyone had imagined. Kepler's first law of planetary motion, that planets move in elliptical orbits with the Sun at one focus, was followed by his second law, which described how planetary motion varied along these elliptical paths. A planet moves faster when it is closer to the Sun and slower when it is farther away, but in such a way that the planet sweeps out equal areas in equal times. This law implied that some force emanating from the Sun was influencing planetary motion, growing stronger as a planet approached the Sun and weaker as it moved away. 10 years later, Kepler announced his third law, which revealed a precise mathematical relationship between a planet's orbital period and its distance from the Sun. The square of the orbital period was proportional to the cube of the average distance from the Sun. This law suggested that whatever force governed planetary motion operated according to strict mathematical principles that could be expressed in simple equations. As you allow yourself to sink deeper into restful slumber, consider the profound implications of Kepler's discovery. The universe was not only orderly, but followed mathematical laws that the human mind could comprehend. While Kepler was revolutionizing astronomy with his analysis of planetary motion, another revolution was taking place in Italy, where Galileo Galilei was turning the newly invented telescope toward the heavens. Born in Pisa in 1564, Galileo had initially studied medicine before turning to mathematics and natural philosophy. He was already famous for his work on motion and mechanics when news of the telescope reached Italy in 1609. Within months, Galileo had constructed his own improved version of the instrument and was making discoveries that would transform our understanding of the cosmos. Through his telescope, Galileo saw that the moon was not a perfect, smooth sphere as ancient philosophers had believed, but a world of mountains and valleys much like the Earth. He discovered 4 moons orbiting Jupiter, proving that not all celestial bodies revolved around the Earth. He observed the phases of Venus, which could only be explained if Venus orbited the Sun rather than the Earth. Most remarkably, he saw that the Milky Way was composed of countless individual stars, revealing the vast scale of the universe for the first time. These telescopic discoveries provided powerful support for the Copernican system, but they also raised new questions about the nature of motion and the forces that governed celestial and terrestrial phenomena. If the Earth was indeed moving through space, spinning on its axis and orbiting the Sun, why didn't objects fall sideways as the Earth rotated beneath them? Why didn't the atmosphere get left behind as the Earth moved through its orbit? These questions could only be answered by developing a new understanding of motion and the forces that governed it. Galileo's work on terrestrial motion was as revolutionary as his astronomical discoveries. Through careful experiments with rolling balls and falling objects, he showed that Aristotle's ideas about motion were fundamentally incorrect. Heavy objects did not fall faster than light ones, as Aristotle had claimed. Instead, in the absence of air resistance, all objects fell at the same rate, regardless of their weight. This principle, known as the equivalence of gravitational and inertial mass, would later become a cornerstone of Einstein's theory of general relativity. Galileo also discovered the law of inertia, the principle that objects in motion tend to stay in motion unless acted upon by an external force. This concept helped explain why we don't feel the Earth's motion through space. From our perspective on the Earth's surface, we are moving along with the planet, so we don't experience the effects of this motion any more than passengers on a smoothly sailing ship feel the ship's movement through the water. As the night wraps you in its gentle embrace, imagine Galileo in his workshop in Padua, rolling bronze balls down inclined planes and timing their motion with water clocks, laying the foundation for our modern understanding of gravity and motion. Galileo's support for Copernican astronomy eventually brought him into conflict with the Catholic Church. In 1633, at the age of 69, he was forced to appear before the Roman Inquisition and recant his belief that the Earth moved around the Sun. He spent his final years under house arrest, continuing his scientific work in secret. The trial of Galileo became a symbol of the conflict between scientific progress and religious orthodoxy, but it also demonstrated the power of the new scientific method to challenge established beliefs through careful observation and mathematical analysis. The work of Kepler and Galileo had shown that the motions of celestial and terrestrial objects followed mathematical laws, but these laws remained disconnected pieces of a larger puzzle. Kepler had discovered how planets moved, but could not explain why they moved as they did. Galileo had revealed the principles governing motion on Earth, but had not connected these principles to celestial phenomena. The synthesis that would unite these insights into a comprehensive theory of universal gravitation would have to wait for the genius of Isaac Newton. Isaac Newton was born on Christmas Day 1642, the same year that Galileo died, in the small English village of Woolsthorpe. His birth occurred during one of the most turbulent periods in English history, as the country was torn apart by civil war between the forces of King Charles I and Parliament. Newton's father, a yeoman farmer, had died before Isaac's birth, and his mother remarried when he was 3 years old, leaving young Isaac to be raised by his grandmother. This early experience of loss and abandonment may have contributed to the solitary, often difficult personality that would characterize Newton throughout his life. Newton's extraordinary intellectual gifts were apparent from an early age, though he showed little interest in farming, much to his mother's dismay. He was fascinated by mechanical devices and spent hours constructing elaborate sundials, water clocks, and model windmills. At the age of 17, he was sent to Trinity College, Cambridge, where he would spend most of the next 3 decades of his life. Cambridge in the 1660s was still dominated by Aristotelian natural philosophy, but Newton had access to the works of more modern thinkers like Galileo, Kepler, and René Descartes. In 1665, when Newton was 23 years old, the Great Plague struck London and spread to Cambridge, forcing the university to close. Newton returned to his mother's home in Woolsthorpe, where he spent the next 18 months in an extraordinarily productive period of scientific discovery. During this miracle year, as it came to be known, Newton developed the fundamental ideas that would revolutionize mathematics, physics, and astronomy. He invented the mathematical technique of calculus, discovered that white light was composed of colours that could be separated with a prism, and began to formulate his theory of universal gravitation. The story of Newton and the falling apple is one of the most famous in the history of science, though it may be more legend than fact. According to various accounts, Newton was sitting in his garden at Woolsthorpe when he saw an apple fall from a tree and began to wonder what force caused it to fall. Whether or not this particular incident occurred, it captures an essential truth about Newton's genius: his ability to see connections between seemingly unrelated phenomena and to ask the right questions about the fundamental nature of physical reality. Newton realized that the force that caused the apple to fall toward the Earth might be the same force that kept the Moon in its orbit around the Earth. This insight was revolutionary, for it suggested that the same physical laws governed both terrestrial and celestial phenomena. If this were true, then the mysterious force that Kepler had inferred from his study of planetary motion was not some special celestial influence, but simply an extension of the familiar force of gravity that we experience on Earth. To test this hypothesis, Newton needed to calculate whether the force of gravity, diminishing with distance according to some mathematical rule, could account for the Moon's orbital motion. He knew from Galileo's work that objects near the Earth's surface fell with an acceleration of about 32 feet per second per second. He also knew the Moon's distance from Earth and the time it took to complete one orbit. Using these values, he could calculate the acceleration required to keep the Moon in its circular path and compare it to what would be expected if gravity followed an inverse square law. That is, if the force decreased as the square of the distance increased. The calculation was complicated by Newton's imperfect knowledge of the Earth's size and the Moon's distance, but when he refined his estimates, the agreement was remarkably close. The same force that pulled the apple to the ground was indeed responsible for the Moon's orbital motion, but its strength decreased with the square of the distance. This was Newton's law of universal gravitation. Every particle of matter in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. As you drift deeper into peaceful sleep, consider the profound implications of Newton's discovery. The universe was revealed to be a vast clockwork mechanism, governed by simple mathematical laws that applied equally to falling apples and orbiting planets, to the tides in the ocean and the motions of distant comets. The same gravitational force that kept our feet on the ground also held the entire solar system together and governed the motions of stars and galaxies throughout the cosmos. Newton's law of gravitation could explain not only the Moon's orbit, but also Kepler's three laws of planetary motion. The elliptical orbits of the planets, their varying speeds, and the relationship between orbital periods and distances all emerged naturally from Newton's equations. For the first time in history, the seemingly chaotic motions of the planets could be predicted with mathematical precision. Newton showed that a comet's path could be calculated from a few observations, that the tides were caused by the gravitational pull of the Moon and Sun, and that the Earth's shape was slightly flattened at the poles due to its rotation. The mathematical framework that Newton developed to describe gravitational forces required the invention of new mathematical techniques. Working independently of the German mathematician Gottfried Leibniz, Newton developed the calculus, a powerful method for analysing rates of change and calculating areas under curves. This mathematical tool was essential for solving the complex problems of orbital mechanics and would become one of the most important mathematical discoveries in history. Newton's masterwork, Mathematical Principles of Natural Philosophy, known as the Principia, was published in 1687 with the financial support of his friend Edmund Halley, the astronomer for whom Halley's comet is named. The Principia presented a complete mathematical description of motion and gravitation that united terrestrial and celestial mechanics in a single theoretical framework. Written in Latin and filled with geometric proofs and mathematical demonstrations, it was accessible to only the most skilled mathematicians of the time, but its impact on scientific thought was immediate and profound. The Principia established the foundations of classical mechanics that would dominate physics for the next 2 centuries. Newton's 3 laws of motion, the law of inertia, the relationship between force and acceleration, and the principle of action and reaction, provided a complete description of how objects move under the influence of forces. Combined with the law of universal gravitation, these principles could explain virtually every observed motion in the heavens and on Earth. Newton's theory was not immediately accepted by all natural philosophers. Some, particularly followers of René Descartes, objected to the concept of action at a distance, the idea that objects could influence each other across empty space without any intervening medium. How could the Sun exert a gravitational force on the Earth across 93 million miles of vacuum? Newton himself was troubled by this question and suggested that gravity might be transmitted through some subtle medium that filled all space. But he was careful to distinguish between his mathematical description of gravitational effects and any speculation about the underlying mechanism. Despite these philosophical objections, the predictive power of Newton's theory gradually won over the scientific community. When Halley used Newton's methods to predict the return of the comet that now bears his name, and when the comet appeared on schedule in 1758, 16 years after Halley's death, it provided dramatic confirmation of Newtonian mechanics. Other successes followed. The discovery of the planet Neptune in 1846 was based on calculations of gravitational perturbations in the orbit of Uranus, and the precise measurement of stellar parallax in the 19th century confirmed that the Earth indeed orbited the Sun. The implications of Newton's work extended far beyond astronomy and physics. His success in reducing the complexity of natural phenomena to simple mathematical laws inspired the Enlightenment belief that human reason could unlock the secrets of nature and society. Philosophers like Voltaire popularized Newton's ideas, presenting them as evidence for a rational, ordered universe governed by discoverable natural laws. The image of the universe as a great machine operating according to precise mathematical principles became a dominant metaphor for understanding not only the physical world, but also human society and behavior. As the 18th century progressed, mathematicians and physicists refined and extended Newton's work. Leonhard Euler, Joseph Louis Lagrange, and Pierre-Simon Laplace developed more sophisticated mathematical techniques for solving gravitational problems and showed that Newton's laws could account for even subtle effects like the perturbations in planetary orbits caused by the gravitational influence of other planets. Laplace, in particular, demonstrated that the solar system was stable over long periods of time, with any small perturbations being self-correcting rather than cumulative. The precision of Newtonian mechanics reached its zenith in the work of 19th century astronomers, who could predict the positions of planets, moons, and comets with extraordinary accuracy. The discovery of Neptune in 1846 represented perhaps the greatest triumph of theoretical astronomy. When observations revealed that Uranus was not following its predicted orbit exactly, mathematicians Urbain Le Verrier in France and John Couch Adams in England independently calculated that the perturbations could be explained by the gravitational influence of an unknown planet beyond Uranus. When astronomers turned their telescopes to the predicted location, they found Neptune almost exactly where the calculations had indicated it should be. Yet even as Newtonian mechanics achieved these spectacular successes, careful observations were revealing small discrepancies that could not be explained within the classical framework. The orbit of Mercury, the innermost planet, showed a tiny but measurable precession, a gradual rotation of its elliptical orbit that was slightly larger than what Newton's theory predicted. This discrepancy, amounting to only 43 seconds of arc per century, was far too small to threaten the overall validity of Newton's laws, but it hinted at the existence of phenomena beyond the scope of classical mechanics. As you allow the gentle currents of sleep to carry you deeper into rest, Imagine the night sky as Newton might have seen it from his garden at Woolsthorpe, not as a mysterious realm of divine perfection, but as a vast laboratory where the same forces that shaped his earthly experience were playing out on a cosmic scale. The apple falling from the tree and the moon sailing across the star-filled sky were both dancers in the same cosmic ballet, their movements choreographed by the invisible hand of gravitational attraction. The 19th century also saw the beginning of new questions about the nature of gravity itself. While Newton's mathematical description of gravitational effects was extraordinarily successful, it said nothing about what gravity actually was or how it worked. Newton had been careful to avoid speculation about the mechanism of gravitational attraction, famously declaring, "I frame no hypotheses about the cause of gravity." But as physics developed, this limitation became increasingly problematic. The development of the theory of electromagnetism in the 19th century, culminating in James Clerk Maxwell's equations, provided a model for how forces might be transmitted through space. Electric and magnetic fields could be understood as disturbances in an electromagnetic field that propagated at the speed of light. This suggested that gravity, too, might be transmitted by some kind of field, but attempts to develop a field theory of gravity along electromagnetic lines were unsuccessful. The most serious challenge to Newton's theory came not from astronomy, but from a seemingly unrelated area of physics: the study of light and electromagnetic radiation. In the late 19th century, physicists were puzzled by the failure of experiments to detect the Earth's motion through the hypothetical ether, the medium that was supposed to carry light waves. The Michelson-Morley experiment of 1887 showed that the speed of light was the same in all directions, regardless of the Earth's motion through space. This result was incompatible with the classical understanding of space and time as absolute and independent entities. The resolution of this puzzle came from a young German physicist named Albert Einstein, who in 1905 proposed his special theory of relativity. Einstein showed that space and time were not separate, absolute entities, but were interconnected aspects of a four-dimensional space-time continuum. The speed of light was constant, not because light moved through a stationary ether, but because space and time themselves adjusted to preserve this constancy. This insight had profound implications for our understanding of gravity and motion. Special relativity successfully explained electromagnetic phenomena and resolved the puzzle of the Michelson-Morley experiment, but it was incompatible with Newton's theory of gravity. In Newton's theory, gravitational attraction was instantaneous. If the sun suddenly disappeared, the Earth would immediately feel the loss of gravitational attraction and fly off into space. But special relativity showed that no influence could travel faster than the speed of light. How could gravity propagate at the speed of light while still maintaining the precise mathematical relationships that Newton had discovered? Einstein spent the next 10 years developing a new theory of gravity that would be compatible with special relativity. The result, published in 1915, was his general theory of relativity, a completely new understanding of gravity as a curvature of space-time itself. In Einstein's theory, massive objects like the Sun and planets do not exert gravitational forces in the conventional sense. Instead, they warp the geometry of space-time, and other objects follow the straightest possible paths through this curved space-time. What we perceive as gravitational attraction is actually the tendency of objects to follow geodesics, the four-dimensional equivalent of straight lines, through curved space-time. This geometric interpretation of gravity was as revolutionary as Newton's original insight 3 centuries earlier. Just as Newton had shown that the same force governed both terrestrial and celestial phenomena, Einstein showed that gravity was not a force at all, but rather a manifestation of the geometry of the universe itself. The planets orbited the Sun not because they were pulled by gravitational attraction, but because they were following the straightest possible paths through the curved space-time created by the Sun's mass. General relativity made several predictions that differed slightly from those of Newton's theory. The orbit of Mercury should precess slightly more than Newton's theory predicted. Light should be bent when it passed near massive objects, and time should run more slowly in strong gravitational fields. All of these predictions were confirmed by observation, with the bending of starlight during a solar eclipse in 1919, providing the most dramatic early confirmation of Einstein's theory. The success of general relativity did not diminish Newton's achievement, but rather placed it in a broader context. Newton's laws remained valid as an excellent approximation for most practical purposes, just as they had been for 2.5 centuries. The corrections introduced by general relativity were significant only for objects moving at very high speeds or in very strong gravitational fields. For everyday phenomena, from the motion of projectiles to the orbits of planets, Newton's equations continued to provide accurate predictions. As the 20th century progressed, general relativity revealed new aspects of gravity that Newton could never have imagined. The theory predicted the existence of gravitational waves, ripples in space-time itself that would be produced by accelerating masses. These waves, finally detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, opened a new window on the universe, allowing astronomers to observe cosmic events like the collision of black holes and neutron stars. General relativity also predicted the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. These exotic objects, once considered merely theoretical curiosities, are now known to exist throughout the universe, with supermassive black holes residing at the centers of most galaxies. The study of black holes has revealed deep connections between gravity, thermodynamics, and quantum mechanics that continue to challenge our understanding of the fundamental nature of reality. The modern understanding of gravity extends far beyond the solar system to encompass the structure and evolution of the entire universe. Observations of distant galaxies have revealed that the universe is expanding, with galaxies moving away from each other at speeds proportional to their distances. This expansion, first discovered by Edwin Hubble in the 1920s, can be understood within the framework of general relativity as a consequence of the overall geometry of spacetime. Even more surprising, recent observations have shown that the expansion of the universe is accelerating, driven by a mysterious component called dark energy that makes up about 70% of the total energy density of the universe. Dark energy appears to have a repulsive gravitational effect, causing the expansion to speed up rather than slow down, as would be expected from the gravitational attraction of ordinary matter. As you drift deeper into the peaceful realm of sleep, contemplate this cosmic mystery. The same force that holds us to the Earth and keeps the planets in their orbits may be engaged in a cosmic struggle with an unknown form of energy that is pushing the universe apart. The quest to understand gravity has also revealed the existence of dark matter, another mysterious component of the universe that makes up about 25% of its total mass energy. Dark matter interacts gravitationally with ordinary matter, but does not emit, absorb, or reflect light, making it invisible to direct observation. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters, which move as if they contained much more mass than can be accounted for by visible stars and gas. The nature of dark matter remains one of the greatest unsolved problems in physics. It may consist of exotic particles that have not yet been discovered, or it may require a modification of our understanding of gravity itself. Some physicists have proposed that the apparent effects of dark matter might be explained by changes to the laws of gravity on very large scales, but these alternative theories have not been as successful as the dark matter hypothesis in explaining the full range of astronomical observations. As we move deeper into the 21st century, the study of gravity continues to reveal new mysteries and possibilities. Physicists are working to develop a quantum theory of gravity that would unite general relativity with quantum mechanics, the theory that describes the behavior of matter and energy on the smallest scales. This quest has led to new ideas about the fundamental nature of space and time, including the possibility that they may not be continuous, but rather composed of discrete units at the smallest scales. String theory, one of the leading candidates for a quantum theory of gravity, suggests that all fundamental particles and forces, including gravity, arise from the vibrations of tiny, one-dimensional strings in a space-time with additional dimensions beyond the familiar 3 dimensions of space and 1 of time. While string theory remains highly speculative and has not yet made predictions that can be tested experimentally, it has provided new insights into the mathematical structure of gravity and its relationship to other fundamental forces. Other approaches to quantum gravity, such as loop quantum gravity, propose that space-time itself has a discrete, granular structure at the smallest scales. According to this theory, the smooth curvature of space-time described by general relativity emerges as an average over these quantum fluctuations, much as the smooth surface of a body of water emerges from the chaotic motion of individual molecules. The technological applications of our understanding of gravity have been as remarkable as the scientific discoveries themselves. The Global Positioning System, which provides navigation information to billions of users around the world, must account for both special and general relativistic effects to maintain its accuracy. Time runs slightly faster in the satellites orbiting high above the Earth than it does on the surface due to both their motion and the weaker gravitational field at their altitude. Without corrections for these effects, GPS would accumulate errors of several miles per day. Space exploration has provided countless confirmations of our understanding of gravity while opening new frontiers for investigation. The precise trajectories of spacecraft visiting other planets depend on detailed calculations of gravitational influences, not only from the Sun and planets, but also from their moons and even asteroids. The Voyager spacecraft, launched in the 1970s, used gravitational slingshot maneuvers around Jupiter and Saturn to gain the speed necessary to reach the outer planets and eventually leave the solar system entirely. More recent missions have pushed the boundaries of gravitational science even further. The Gravity Probe B satellite, launched in 2004, confirmed Einstein's prediction that a rotating massive object should drag space-time along with it, an effect called frame dragging. The European Space Agency's LISA Pathfinder mission has tested technologies for detecting gravitational waves from space, where the absence of terrestrial vibrations will allow for even more sensitive measurements than are possible on Earth. As you allow yourself to settle into deeper rest, imagine the vast network of gravitational influences that surrounds us at every moment. The Earth pulls us downward with steady, familiar force. But we are also subject to the gravitational attraction of the Moon, causing subtle variations in our weight as our satellite passes overhead. The Sun's gravity reaches across 93 million miles to hold our planet in its orbit, while the gravity of Jupiter, despite its enormous distance, creates measurable perturbations in the orbits of asteroids and comets. The story of gravity's discovery reveals humanity's gradual recognition of the deep unity underlying natural phenomena. What began as separate questions about falling objects and planetary motions evolved into a comprehensive understanding of the fundamental structure of space, time, and matter. Each generation of scientists built upon the work of their predecessors, gradually constructing a theoretical edifice of extraordinary power and beauty. The ancient Greeks wondered why objects fell toward the earth while the stars remained fixed in the heavens. They could not have imagined that the same force responsible for both phenomena would eventually be understood as a curvature in the fabric of space-time itself, propagating at the speed of light and giving rise to some of the most exotic objects in the universe. The mathematical equations that describe gravity have revealed black holes, gravitational waves, and the expanding universe, phenomena that stretch our understanding of reality to its limits. Yet for all its mathematical sophistication, our modern understanding of gravity remains incomplete. The attempt to reconcile general relativity with quantum mechanics has revealed deep puzzles about the nature of space and time at the smallest scales. The discovery of dark matter and dark energy has shown that we understand only a small fraction of the universe's total contents. These mysteries ensure that the story of gravity's discovery is far from over. The philosophical implications of our understanding of gravity continue to resonate through human culture. Newton's clockwork universe gave way to Einstein's relativistic cosmos, where space and time are malleable and gravity arises from geometry rather than force. This shift in perspective has influenced not only science but also art, literature, and philosophy. The realization that we live in a universe where time can slow down, space can curve, and matter can warp the very fabric of reality has challenged our most basic assumptions about the nature of existence. In the laboratories of today, physicists continue to probe the mysteries of gravity with ever more sophisticated instruments. Gravitational wave detectors can sense distortions in space-time smaller than 1/10,000th the width of a proton. Atomic clocks are precise enough to measure the gravitational redshift, the slowing of time in a gravitational field, over height differences of just a few centimeters. These experiments continue to confirm the predictions of general relativity while searching for signs of new physics beyond Einstein's theory. The Large Hadron Collider and other particle accelerators probe the fundamental structure of matter and energy, seeking to understand how gravity relates to the other fundamental forces of nature. At the enormous energies achieved in these machines, physicists hope to create conditions similar to those that existed in the first moments after the Big Bang, when gravity may have been unified with the electromagnetic and nuclear forces in a single, all-encompassing interaction. As the night deepens around you and consciousness gently fades, consider the remarkable journey that has brought us to our current understanding of gravity. From the first human who wondered why objects fall to the ground, to the sophisticated theories and experiments of modern physics, this quest has revealed the profound interconnectedness of all things in the universe. The force that shapes our daily experience on Earth is the same force that ignites stars, forms galaxies, and drives the evolution of the cosmos itself. The story of gravity's discovery is ultimately a story about human curiosity and the power of reason to unlock the secrets of nature. It demonstrates how seemingly simple questions can lead to profound insights about the fundamental structure of reality. Each generation of scientists has added to our understanding, building upon the work of those who came before while opening new avenues for future exploration. In the coming decades, new technologies and theoretical insights will undoubtedly deepen our understanding of gravity and its role in the universe. Space-based gravitational wave detectors will observe cosmic events billions of light-years away. Quantum computers may help solve the mathematical complexities of quantum gravity. Advances in cosmology may reveal the true nature of dark matter and dark energy, and perhaps uncover new aspects of gravitational physics that we cannot yet imagine. The quest to understand gravity has been one of humanity's greatest intellectual adventures, spanning cultures, centuries, and continents. From the ancient astronomers of Babylon to the theoretical physicists of today, countless individuals have contributed to this ongoing story of discovery. Their work has revealed not only the nature of gravity, but also something profound about the universe itself, that beneath its apparent complexity lies a deep mathematical beauty that the human mind can comprehend and appreciate. As you drift into peaceful sleep, surrounded by the gentle embrace of Earth's gravitational field, remember that you are part of this cosmic story. The same physical laws that govern the fall of an apple and the orbit of the moon also govern the beating of your heart and the firing of neurons in your brain. You are not separate from the universe, but intimately connected to it through the fundamental forces that shape all matter and energy. The invisible threads of gravitational attraction that connect every particle of matter in the universe also connect you to the stars. The calcium in your bones was forged in the nuclear fires of ancient supernovas, scattered through space by gravitational collapse and explosion, and eventually gathered by gravity into the solar system where life could emerge and flourish. You are, quite literally, made of stardust, held together by the same force that holds the cosmos in its grand design. In this final saga of gravity's story, we find ourselves at a unique moment in cosmic history. We live in an era when humanity has developed the scientific tools and theoretical understanding necessary to perceive the universe as it truly is, not as a collection of separate, unrelated phenomena, but as a single, integrated system governed by elegant mathematical laws. We can trace the influence of gravity from the quantum realm to the largest structures in the universe, understanding how this fundamental force has shaped everything from the formation of atoms to the evolution of galaxies. The story of gravity's discovery reminds us that the universe is not random or chaotic, but follows deep patterns that reward careful study and contemplation. The same mathematical relationships that describe the motion of planets also appear in the behavior of atoms, the structure of crystals, and the flow of fluids. This underlying unity suggests that reality itself has a fundamentally mathematical nature, that the universe is not only stranger than we imagine, but more beautiful and more interconnected than we had ever dared to hope. As consciousness fades and sleep embraces you completely, let your mind rest in the knowledge that you are cradled not only by the familiar comfort of your bed, but by the vast, invisible network of gravitational influences that permeate all of space and time. The force that pulls you gently toward the Earth also guides the dance of galaxies billions of light years away, ensuring that the cosmos remains bound together in an eternal embrace of mutual attraction. The story of gravity's discovery continues even now in laboratories and observatories around the world, where scientists are probing ever deeper into the mysteries of space, time, and matter. Future generations will undoubtedly uncover new aspects of gravity's influence and perhaps develop theories that go beyond even Einstein's remarkable insights. But the fundamental truth revealed by this long journey of discovery will remain: that we live in a universe where everything is connected to everything else through the subtle but pervasive influence of gravitational attraction. In the end, the story of how gravity was discovered is not just a chronicle of scientific progress, but a testament to the power of human wonder and curiosity. It began with the simple observation that objects fall toward the Earth, and culminated in the realization that gravity is woven into the very fabric of space-time itself. This journey of understanding has taken us from the surface of our planet to the edge of the observable universe, revealing the profound unity that underlies all natural phenomena. As you drift deeper into the peaceful realm of sleep, carry with you the knowledge that you are part of this grand cosmic story, a conscious being capable of understanding the very forces that created and sustain you. In your dreams, perhaps you will soar beyond the pull of Earth's gravity, traveling to distant worlds where different gravitational environments create landscapes and possibilities that we can barely imagine. And when you wake, you will return to a world where gravity continues its ancient work, holding everything together with invisible threads of attraction that bind the universe in a web of mathematical beauty and profound connection. The gentle force that has drawn your eyelids closed and pulls your body toward rest is the same force that shapes the destiny of stars and galaxies, that governs the ebb and flow of tides, and that will continue to influence the evolution of the cosmos long after our sun has burned out and our planet has returned to cosmic dust. In understanding gravity, we have glimpsed something eternal and universal, a principle that transcends individual lives and even entire civilizations, connecting us to the deepest patterns of existence itself. Sleep now, cradled by gravity's gentle embrace, knowing that you are part of the greatest story ever told, the story of how the universe came to understand itself through the patient work of human minds seeking to comprehend the forces that govern all things. In your rest, you join the eternal rhythm of cosmic motion, the dance of matter and energy that has continued for billions of years and will continue for billions more, guided always by the invisible hand of gravitational attraction that holds everything together in perfect mathematical harmony.